5G and 6G mobile cellular network. Here's a structured explanation of 5G and 6G, including their architecture, technologies, use cases, and evolution. 5G, 5th generation mobile networks. Definition: 5G is the 5th generation mobile communication standard, designed to provide ultra-high-speed data, low latency, massive connectivity, and support for new applications like IoT, AR/VR, and autonomous systems. 5G is not just a faster version of 4G, it is a fundamental redesign of the entire network architecture. While 4G was about mobile broadband, 5G is a service-oriented platform designed to connect everything from smartphones to autonomous cars and industrial sensors. The two deployment modes. When 5G was first launched, operators didn't just flip a switch. They used two distinct paths: non-standalone, NSA. This was the quick start mode. It uses the existing 4G core, EPC, but adds 5G antennas. Your phone uses 4G for the control handshake and 5G for the fast data speeds. Standalone, SA. The true 5G. This involves a brand new 5G core, 5GC. It is entirely independent of 4G, allowing for the lowest possible latency and advanced features like network slicing. Key technology pillars: 5G relies on several breakthrough technologies to achieve its massive speeds and reliability: mmWave, mmWave high-frequency bands, 24 GHz+, that offer massive capacity but short range. It's the super-fast 5G you find in stadiums or city centers. Massive MIMO: instead of a few antennas on a tower, 5G uses hundreds. This allows the tower to talk to dozens of devices simultaneously on the same frequency. Beamforming: unlike 4G, which broadcasts a signal everywhere, like a floodlight, 5G focuses a specific beam of energy directly at your phone, like a laser pointer. This reduces interference and saves power. Network slicing: this allows an operator to slice the physical network into multiple virtual ones. For example, one slice can be dedicated to emergency services, ultra-reliable, while another is for smart meters, low data, high volume. The 5G core, 5GC, functions in 4G. We had nodes like the MDAM and SGW. In 5G, these are replaced by software-based network functions, NFS. 5G function equivalent in 4G role AMF, access and mobility. MDAM manages registration and tracking of the device. SMF, session management. MDAM/PGW handles the IP address and session setup. UPF, user plane function. SGW/PGW, the data highway where your internet traffic actually travels. UDM, unified data management. HSS, the central cloud database for user profiles. PCF, policy control. PCRF manages rules for charging and quality of service. Voice in 5G, VoNR. In 5G standalone networks, the voice service is called VoNR, Voice over New Radio. Just like VoLTE, VoNR still uses the IMS core to manage the call. However, because it runs natively on the 5G core, you get faster call setup times, almost instant, and the ability to maintain full 5G data speeds even while you are talking on the phone. Fun fact: because 5G is so fast and has such low latency, it can handle holographic calls or real-time translation during a voice conversation, provided the application servers in the IMS core are upgraded to support them. 1.1 Key objectives of 5G enhanced mobile broadband: eMBB, very high data rates, up to 10 to 20 Gbps peak, ultra-reliable low-latency communication, URLLC latency 1 millisecond for critical applications, massive machine-type communication, mMTC support, millions of IoT devices per km, superscript 2 network slicing, logical networks on a shared physical infrastructure, all IP architecture, continuation of LTE EPC, integrating with IMS for voice/multimedia. The objectives of 5G are often visualized as a triangle of services, with each corner representing a radical improvement over 4G. Beyond these three service pillars, 5G introduces structural changes like network slicing and an all-IP architecture to manage them. Enhanced mobile broadband, eMBB, objective: to provide high bandwidth, high-speed internet that feels like fiber optic speed on a mobile device. Peak data rates, target of 10 to 20 Gbps, roughly 100x faster than 4G. Capacity, support for 10,000x more total network traffic than previous generations. Use cases: 4K/8K video streaming, augmented reality, AR, virtual reality, VR, and high-speed access in crowded areas like stadiums. Ultra-reliable low latency, URLLC, objective: to enable near-instantaneous communication for mission-critical applications where failure is not an option. Latency, target of less than 1 millisecond, the time it takes for data to travel between points. Reliability, achieving 99.999%, the 5 nines, success rate for data delivery. Use cases: autonomous driving, V2X, remote robotic surgery, and real-time control of industrial factory robots. Massive machine-type communication, mMTC, Objective, to connect the Internet of Things, IoT, on a massive scale without draining battery life or crashing the network. Connection density, support for 1 million devices per square kilometer, 10x more than 4G. Efficiency, designed for small data packets and low power, allowing device batteries to last up to 10 years. Use cases, smart cities, parking sensors, streetlights, smart agriculture, and utility meters. Network slicing objective, to transform a single physical network into multiple virtual networks tailored to specific needs. Dynamic resource allocation, instead of a one-size-fits-all network, an operator can slice a portion of the bandwidth and dedicate it solely to URLLC, for ambulances, while another slice handles eMBB, for consumer Netflix streaming. Isolation, if the consumer slice gets congested, the emergency slice remains unaffected, guaranteeing a specific service level agreement, SLA, for each use case. All IP architecture, service-based architecture, objective, to move away from rigid, proprietary hardware and toward a flexible, software-defined cloud environment. Virtualization, traditional hardware nodes are replaced by virtual network functions, VNFs. This allows the network to be upgraded or scaled via software updates rather than physical hardware replacement. Unified language, by using IP, Internet Protocol, and APIs for all communications, 5G can seamlessly integrate with web services, private enterprise clouds, and the IMS core for voice. 1.25G architecture. A radio access network, RAN, GNB, next-gen Node B 5G base station supports NR, new radio sub 6 GHz and mmWave, 24 to 100 GHz, frequencies massive MIMO beamforming off-MOF or DL/L in a 5G network. The GNB, next generation Node B, is the 5G equivalent of 4G's eNode B. It is the radio base station that communicates with your phone, UE, using 5G new radio, NR, technology. While the 4G eNode B was a monolithic unit, hardware and software in one box, the GNB is designed to be modular, virtualized, and split, allowing it to handle the massive speeds and low latency required by 5G. 1. The disaggregated architecture, CU2 split. One of the most significant changes in 5G is that a GNB can be split into different functional parts. This allows the brains of the tower to be moved to a data center while the antennas stay on the pole. CU, centralized unit. The non-real-time part. It handles high-level signaling and security. 1. CU can control many DUS. DU, distributed unit. The part that handles real-time tasks like scheduling and error correction. It is usually located closer to the antennas. RU, radio unit. The physical hardware and antennas that convert digital bits into radio waves. 2. Key responsibilities of the GNB. The GNB is much smarter than its predecessors. Its primary roles include beamforming and massive MIMO. Instead of broadcasting a signal in all directions, the GNB uses advanced math to point a dedicated beam of energy directly at your device, increasing speed and reducing interference. Network slicing support. The GNB can distinguish between a mission-critical signal, like an ambulance, and a standard data signal, like a YouTube video, and prioritize the radio resources accordingly. Dual connectivity. The GNB can work alongside a 4G eNode B. Your phone can download data from both 4G and 5G at the same time to maximize speed. This is known as NDC. 3. The GNB interfaces. The GNB connects to the rest of the world through 3 primary interfaces. Interface connection purpose. N2 GNB rightward arrow AMF the control path. Send signaling to the 5G core. N3 GNB rightward arrow UPF the data path. Carries your actual internet and voice traffic. XN GNB left right arrow GNB allows neighboring 5G towers to talk to each other for handovers. F1 CU left right arrow do the internal interface that allows the split GNB parts to communicate. 4. The GNB and voice, VoNR, when you make a call on 5G, voice over new radio, the GNB plays a crucial role in maintaining quality. 1. The GNB receives instructions from the 5G core, SMF/PCF, that a voice session is starting. 2. The GNB allocates a dedicated flow for voice, ensuring these packets get a higher priority level than your background apps. 3. Because the GNB has lower latency than 4G, your call connects significantly faster, often in less than 2 seconds. B Core Network, 5G Core, 5GC, fully service-based, cloud-native, and modular key functions, AMF, access and mobility management function mobility, registration SMF, session management function session control, IP allocation UPF, user plane function forwarding user traffic, QoS enforcement. PCF, policy control function policy and charging control AUSF/UDM, subscriber authentication and data management supports network slicing for different services on the same infrastructure. 5G architecture diagram, simplified, UE, smartphone/IoT, NR, 5G air interface, V plus dash dash plus G and B plus dash 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 plus dash 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 plus N2 slash N3 V plus dash 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 plus dash 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 plus 5G CAMF, SMF, UPF plus dash 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 plus dash 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 plus V Internet slash Cloud Services slash IMS. 1.3 Key features of 5G feature description: peak data rate DL, 10 to 20 Gbps, UL, 10 Gbps latency 1 millisecond for URLLC, 10 ms for eMBB device density up to 1 m devices / km superscript 2 spectrum sub 6 GHz, mmWave, 24 to 100 GHz, network slicing supports multiple virtual networks, reliability 99.999% uptime for critical services. 6G, 6th generation mobile networks, definition: 6G is the next generation network standard, expected 2030, that will go beyond 5G in speed, latency, AI integration, and immersive communication. 2.1 Key objectives of 6G: terabit data rates, up to 1 Tbps peak in some scenarios, sub-millisecond latency, 0.1 milliseconds for real-time holographic communications, integration of AI/ML in network control, full immersive XR, extended reality, and holographic communications, intelligent and self-organizing networks, integration of space terrestrial networks, satellites, UAVs, HAPS, energy efficiency and sustainability. 2.2 Expected 6G technologies: technology role in 6G terahertz communication, 0.1 to 10 Thz, ultra-high-speed data links, AI/ML-driven network, predictive resource allocation, self-optimization, integrated sensing and communication, ISAC, environment sensing plus communication, holographic telepresence, real-time 3D hologram transmission, quantum communication, ultra-secure encryption, satellite and UAV networks, global coverage, beyond terrestrial limits, blockchain and edge AI, decentralized secure services. 2.3 6G architecture: conceptual, device layer, smartphones, AR/VR/XR devices, IoT nodes, holographic sensors, access layer, terahertz cells, satellite, UAVs, integrated RAN network layer, AI native, service-based architecture, edge computing, cloud-native core service layer, holographic communication, XR, tactile internet, autonomous systems devices, AR/VR, holograms, IoT, terahertz/satellite/UAV, intelligent RAN, AI-driven, AI-native 6G core edge/cloud services, XR, holograms, tactile internet. Key differences: 3G rightward arrow, 4G rightward arrow, 5G rightward arrow, 6G feature, 3G 4G LTE, 5G 6G core network, CS plus PS all IP, EPC, cloud native, 5G CAI native, service-based 384 kbps, 42 peak data rate, 300 Mbps DL, 10 to 20 Gbps, 1 Tbps, theoretical, MBPs latency 100 to 150 milliseconds, 20 to 30 milliseconds, 1 millisecond, 0.1 milliseconds off MA plus NR, mmWave, massive terahertz, ISAC, AI radio tech MA/HSPA MIMO optimized holographic plus voice CS voice volte VoNR/VoIP immersive XR network slicing, AI/ML driven, self-manual EPC plus PCRF management, cloud native. Organizing device density 10K/km superscript 2 100K/km superscript 2 1m/km superscript 2 10m/km superscript 2 plus, IoT and XR. Summary: 5G is about ultra-high speed, low latency, massive IoT, and network slicing. 6G is conceptual, aiming for terabit speeds, AI-native networks, holographic and XR services, global coverage, and intelligent self-organizing systems. Evolution trend: voice rightward arrow, data rightward arrow, multimedia rightward arrow, immersive and intelligent services.